Hello, Ajman University students, third year. The course is Biopharmaceutics and Pharmacokinetics. Today I will talk about intravenous infusion. Let's remember first the assumptions we had for IV bolus administration. In IV bolus administration, we said that we have first order kinetics. The elimination is first order. We talked about one compartment. So in intravenous infusion, the same thing applies. But here, the difference is that the drug is infused into the body over some time. So what are the objectives of intravenous infusion? What you need to know and to be able to deal with after finishing this lecture. One, you need to draw a scheme of the intravenous infusion with first order elimination. Then after doing this scheme, you need to write the differential equation for intravenous infusion. After that, you need to recognize the integrated equation and use that integrated equation to calculate the concentration at any time following intravenous infusion. Also, you will need to calculate from the data of intravenous infusion, you need to calculate KEL, rate of elimination constant, and V, which is the apparent volume of distribution. You already know that multiplying KEL V is giving you the clearance. Clearance is very important. After that, you will recognize that when we administer a drug as infusion, we usually target a certain concentration. And of course, this concentration is within the therapeutic window of the drug. Like, for example, you have time and you have concentration, time in hour, concentration in milligram, for example, per liter. So when you do an infusion, you are trying to reach a concentration that is between minimum effective concentration and minimum toxic concentration. So here, that's where you are trying to achieve. So your infusion rate is actually adjusted so that you will get to this steady state condition. You will discover that getting to this steady state takes a long time. And you cannot wait, for example, for 10 hours, 20 hours just to get to the steady state. So you need to do certain things to make it faster to achieve steady state concentration. So let's go back to intravenous infusion. Why we will use intravenous infusion in the hospitals? Sometimes the patient is already having, for example, parenteral nutrition, يعني infusion bag. في عندنا line, we have a line, tube, that is connected to the patient and he's receiving parenteral nutrition, maybe because he's bedridden or he has coma, etc., etc. So in this case, if the drug does not interact with the other materials in the parenteral nutrition, we could administer the drug along the same line where parenteral nutrition is administered. We call it piggyback. Piggyback. So this is one thing. Another thing, sometimes you wouldn't go for IV bolus administration. Maybe the reason is the quantity is large. Another reason is if you give it all at once, if you give the drug all at once as IV bolus, some toxicity might happen in the beginning. For example, it is known that vancomycin administration of vancomycin quickly can result in what is called red man syndrome. So in this case, we prefer to infuse the drug more slowly. So this is one reason why we might use intravenous infusion. So let's go back now and talk about the intravenous infusion process. Let me draw the scheme for you. So if you remember, in our IV bolus administration, we had one compartment and there is a window, we call it KEL, for the drug to be removed from the body by first order kinetic. Now this applies here as well in intravenous infusion. But additionally, we are having infusion. So the drug is slowly entering the body by a constant rate. So the rate of infusion is constant, not like the rate of elimination. The rate of elimination is first order. So here, the drug gets out depending on the concentration. The higher the concentration in the compartment, the faster it gets out. But the rate of infusion is, as I said, is constant, and I will give it the symbol K0. Now in some textbooks they give it the symbol R. So we will use K0. Now why I am adding 0 here? It's because the process is 0 order. Why is it 0 order? It's because the rate is constant. Bainama this is first order because the rate depends on the concentration. The higher the concentration in the compartment, the faster it goes out. Now remember this scheme because I will now write a differential equation. Before I write this differential equation, I want you to know the units of K0. K0 units is amount per time. مثلا, for example, milligram per minute or milligram per hour. Of course, yes, you are adjusting in the hospital. You are adjusting the infusion rate using the infusion pump. You are adjusting the infusion rate using the infusion pump. And if you are familiar with that, you are adjusting volume per time. That's what happens in the hospital. But this volume that you are adjusting, it's because of the amount of the drug in that volume. So actually K0, it's not volume per time, it's amount of drug per time. This amount of drug will be in that volume. So think about this process. It's actually having not only output like IV bolus administration, all the drug is inside the body at 0 time. No, here we have drug coming in while it's going out. So it's different. So there is, let me say, input and output at the same time happening. So how the concentration changes in the body. So dCP by dt, yani the rate of change in concentration, how is it happening? If you remember with IV bolus administration, we said that it's minus KEL Cp. Because the higher the concentration, the faster it goes out. So this is the output. I will call this minus KEL Cp. This is the output. But at the same time, there is also the input. What is the input? K0. K0 is the input. So I have input positive. This is positive. This adds drug to the body. This is positive, increasing the concentration. And there is negative, which is the rate of elimination. Now the problem here is we have to look at the units. dCP divided by dt is concentration per time. This is also concentration per time. But this is amount per time. It's amount. K0 is amount per time. That's why what we will do is we will try to make them all the same. So how? If I multiply this one, dCP divided by dt, if I multiply it by V, then it will be amount per time. Okay? So this is amount per time. Amount per time, I have to do this amount per time, will be minus K alpha Cp. I have also to multiply it into V. So the scheme that I drew for you, who were one compartment with zero order input and first order output, the one that explains how the changes happen here is in this differential equation. The only thing here we are talking about amounts per time. Instead of concentration per time, this equation shows you how the changes happens amount per time. طيب, you will notice that in the beginning يعني at time zero. At time zero there is no concentration at all. So what is happening at time zero is you are adding drag inside by K0, اللي هو rate of infusion. You are adding a drag. طيب, after that, what happens? Concentration will start to increase. يعني, because concentration is increasing, starting from zero and then increasing, also the output will increase. Because look at the output, it's first order. So the higher the concentration, the higher is the output. So yes, you are adding drag to the body, but with time, the rate of elimination will start to increase until the input is equal to the output. يعني, until minus K alpha Cp V is equal to K0. At that time, you are reaching the steady state. So let us look by drawing a graph. Let's look at how this happens. So this is the graph. You have time and concentration in milligram per liter, and time in hour. So in the beginning, you have zero concentration just when you want to start, and then the concentration starts to increase, but then slowly it starts to level. Why it starts to level at this stage? Because, as I said, the concentration, while it's increasing, the rate of elimination increases until the rate of elimination and rate of input, K0, rate of infusion, becomes equal. At that time, you are reaching what we call CP, not SPS, CPSS, which means the concentration of the drag in the plasma at steady state. Of course, that is your target, and your target should be between the minimum effective concentration and the maximum and the minimum toxic concentration. Right, so what do? You are actually need to adjust the infusion rate to get the steady state concentration. So let us little bit talk about the steady state concentration. We already said that at steady state concentration, the input is equal to the output. يعني, the input is K0 and the output is KEL VB VCB. They are equal. That's why you reach the steady state. Okay, think about it. Steady state means the concentration is not changing. Now, both processes, the input and the output, are equal. So there is no change in the concentration, which means that V dCp divided by dt, this is the change in amount or concentration per time, is equal to 0. So actually, K0 and K alpha V في CP, they are equal at that time. That's why the CP that is here, K0 equal to K alpha V في CP. This CP, I will call it CPSS, the concentration at steady state. So when both are equal, we reach the steady state. According to this equation, your CPSS will be equal to H, K0 divided by KLPV. Now remember that KLPV is the clearance. Okay? Okay, so let me remove this one now. So if I want to target CPSS, I need, for example, 15 milligram per liter. What do I need to know? What do I need to adjust? I need to know the clearance of the drug, KLPV. I need to know that in order to adjust K0, اللي هو rate of infusion. Is that clear? So, knowing CPSS, my target. This is my target. And knowing the clearance of the drug. طبعا the clearance of the drug depends on, على مين? Depends on the drug and the patient. If the patient has liver disease or has kidney problems, the clearance will change. Okay? So, this equation allows you to calculate the rate of infusion in order to obtain the CPSS. طيب, the second part. We already talked about the differential equation that allows you to describe the process, the scheme. Now we need to recognize the integrated equation. So what is the integrated equation? Integrated equation is CP equal to K0 divided by KLPV. طبعا this is ايش هذا K0 على KLPV؟ this is the CPSS. This is multiplied into 1 minus E plus minus KLPV. So look at this equation carefully. So CP is equal to CPSS, كأني بحكي CP0, if you remember. Multiplied في 1 minus E plus minus KLPT. طبعا if you remember in IV bolus administration, كان E plus minus KLPT, it was the fraction of drug remaining in the body. What we are doing, we are building concentration with time until we reach steady state. So the opposite of that is 1 minus E plus minus KLPT. Okay? Actually, it looks similar to CP0, PE plus minus KLPT. Similar. But this one is the opposite. Opposite means before in IV bolus administration we were talking about fraction remaining. Yani with time it's going down, concentration is decreasing. Here it's the opposite. 1 minus E os minus KLPT is the opposite of E os minus KLPT. It's the opposite. If that one decreases with time, 1 minus E os minus KLPT will increase with time. So that's why we have a buildup of concentration. So let us look at this equation. And I want you to imagine what is happening. What happens at time 0? Remember that at time 0, E us minus KLP time 0 is 1. Yani this fraction here is 1. 1 minus 1 is 0. So 0 of CPSS is 0. So at time 0, what is the concentration? What is the concentration in the body when you want to start the infusion? It is 0. Is that clear? So now we recognize the integrated equation, and we found out from the integrated equation that at time 0, the concentration starts with 0. بينما بالIV bolus administration, at time 0, the concentration was the maximum, and then it started to decrease. Here, exactly the opposite is happening. Okay, let's talk about time infinity. So what happens after very, very long time? So in this case, you need to substitute t with infinity, or very, very long number. Okay? So Cp equal to Cpss multiplied 1 minus e to the power of minus very large number. E to the power of minus very large number, as you learned in IV bolus administration, is approximately 0. So what will happen? Cp equal to Cpss multiplied into 1 minus 0. يعني 1. So Cpss multiplied 1, Cpss. So Cp at time infinity, after very, very long time, will be equal to Cpss, and we will reach the steady state. But it seems that you need theoretically very long time to approach that level. Okay, and this is a problem. Now we will talk about an example, and we'll try and solve that together. Okay, the example that we will talk about is regarding a drug, theophylline. Now, theophylline is a drug that is given in case of asthma. The question says the target concentration is 15 milligram per liter. This is our target. And when I say our target, and I'm talking here about IV infusion, it means that this target will be my Cpss, because that is where I want to reach. So 50 milligram is my Cpss. And another given data, T half, which is 4 hours. Another data is the apparent volume of distribution, which is 25 liter. And you are required to calculate K0. Now, you know that Cpss, we discussed this previously, Cpss is equal to K0 divided by KL/V. So everything is given except K0, which I need to calculate, and also KL is not given directly. But if you look at the data given, you are given half-life, which is 4 hours. Therefore, you could calculate KL. How do you calculate KL? KL is equal to 0.693 divided by the half-life, which is 4 hours. So if you do that, the answer will be 0.17 hour to the power of minus 1. So all what you need to do now is calculate K0. We said that Cpss is equal to K0 divided by KL/V. So K0 will be equal to Cpss multiplied KL/V. So K0, the one I need, is equal to Cpss V KEL. How did I get this one? We talked already about the equation of Cpss. Cpss is equal to K0 divided by KL/V. So K0 will be calculated in this way. So what is my Cpss? 15 multiplied. What is my apparent volume of distribution? It's 25 liters. And what is my KL? It's 0.17. So the answer is about 63.8. Now what is the unit of K0? We already said it's amount per time. Okay? But what amount, what time should I use? I will use milligram per hour. Where did I get milligram per hour? Why it's not microgram per minute, for example? Why it is not something else? Remember that 15 is in milligram per liter, so I have milligram. The volume of distribution in liter. So I have no problem, liter here and liter here, there is no problem. They will cancel each other. And 0.17 is per hour. That's why you have milligram per hour. Okay? So that's the unit. Of course, for some pharmacists or nurses, they will find that it's not convenient to use this number 63.8. Either they will make it 65 or 60. Usually they go for the lower because it is safer. But it's not just like that. You need to verify that going to 60 will not give you ineffective concentration. يعني below the minimum effective concentration. We don't want that. That's why you need to do verification. So what happens if I use 60? What will happen to the target, to the CPSS? Of course, it will be less because I reduced the infusion rate. Yani, if I reduce the infusion rate by half, CPSS will reduce by half. But I didn't do that. I just reduced it a little bit from 63.8 to 60. So what is your CPSS? It will be equal to K0. Now I decided to use 60. Population CPSS unknown. It was 15. No, now it's different because I reduced the infusion rate to 60. So it's equal to 60 divided by the clearance in KL to V. KL is 0.17 and V is 25 liter. If you do the calculation, you will get CPSS to be 14.1 milligram per liter. This is the unit of the concentration. Now 14.1 is less than 15, our target. Is that okay? Well, we need to know what is the therapeutic window of theophylline. Theophylline is one of the narrow therapeutic window drug. The minimum effective concentration is 10 and the minimum toxic concentration is 20. So 14.1 looks fine to me. So we will use 60 milligram per hour instead of 63.8. I already told you that the minimum effective concentration of theophylline is 10 hours. It's 10 milligram per liter. It means that if I start the infusion using 60 milligram per hour, it only will give effect when it starts reaching 10 milligram per liter and above then the effect will start. So how long do you think it will take to reach 10 milligram per liter? How long? Is it going to take long time? Because if it's long time, this is no use to us. It means infusion is not effective way of administering the drug. So how long do you think? Can we do the calculation? Yes, we can. Now, what is our target? What is your job to do? Your job to do is to know how long will it take to reach the 10. I am operating at 60 milligram per hour infusion. And the target now is 14.1 because this is my CPSS. So how long until it reaches 10? Because from 10 it will start the effect. Now, which equation do I use? Since this is during infusion, يعني تخيلوا, imagine this is time in hour, and this is your concentration, let's say milligram per liter, and let's say this is your 10 level, and this is your 20 level, okay? Now you start with infusion, and you want to know when you are going to reach this point, at what time, okay? What time you will reach 10 milligram per liter. So this is during infusion, not steady state. Because it's during infusion, I will use Cp equal to CPSS, I will heal K0, divided by KLPV multiplied into 1 minus E os minus KLPV. Now do the math. What will you use here instead of Cp? You are going to use 10 milligram per liter, and you will find out what is the time until you reach 10 milligram per liter. What is this time? Do the calculation, and what will you find? You will find that it takes how long? It takes actually 7. And if you do the calculation, you will find that it takes 7.24 hours to reach the minimum effective concentration. That is too much. That's a lot of time. Yani imagine someone in the bed, and before the drug starts giving the effect, I need more than 7 hours to get to that minimum level. Let us understand more about the time. How much does it take to reach half the CPSS? Not the whole CPSS. Half the CPSS. How long does it take? Okay, so I will explain to you now the time needed to get to half the CPSS. I will call it the accumulation T half. Okay, because that is the time, accumulation T half is the time when I get to half the CPSS. Okay, so remember this equation, Cp is equal to CPSS, which is K0 divided by KLPV multiplied into 1 minus E os minus KLPT. Now I want to get to half the CPSS. So when is this time? So I will write it as half the CPSS is equal to CPSS into 1 minus E os minus KL. Now I will call it T half, accumulation T half, not the elimination T half. CPSS goes with CPSS, so you have half is equal to 1 minus E os minus KL P T half. Okay, so you could arrange, take half to this side, let's say minus half, 1 minus half, and take minus E os minus KL P T half, take it the other side. Okay, so you will have 1 minus half is equal, 1 minus half is equal to E os minus KL P T half. So 1 minus half is half. So half is equal to E os minus KL P T half. Now take ln both sides. You will get minus 0.693 is equal to minus KL P T half. Ln both sides. Of course, negative goes with negative, and then you can calculate T half as equal to 0.693 divided by KL. Strange, right? Because this is the same equation as the elimination half-life. So actually, to get to the half the steady state, I need 1 half-life of the drug. Yani, if my drug has a long half-life, I really will need long time to get to the half the steady state. That's what it is, what it means. In the same way, you could calculate how much it will need to reach 75% of the steady state. 75. Yani we reach 50, okay, that is half the steady state. Then 75. 75 is in the middle between 50 and 100%. So 0.75, 75%, yani 0.75 of the CPSS will be equal to CPSS 1 multiplied 1 minus E equals minus KL 15. So when are we going to reach 75%? If you do the math and you take CPSS with CPSS, then you will get that 0.75 is equal to 1 minus E equals minus KL T. Take 0.75 there, let's say 1 minus 0.75, يعني ربع 0.25, and take minus E equals minus KL T the other side. يصير عندنا what we will get is 0.25 is equal to E to the power of minus KL 50. So this is what I do. In the same way I did it with the half-life. So 0.25 is equal to E to the power of minus KL 50. Take ln both sides. Okay? Take ln both sides. And you will find that actually to reach 0.75 of CPSS, يعني 75% of CPSS, you will need 2 half-lives of the drug. Actually, if you look at this process carefully, you will find that it is exactly the opposite of elimination half-life. يعني في elimination half-life, I need 2 half-lives to reach 25% remaining in the body. صح? Here, to reach 75%, I need 2 half-lives of the drug. In the same way, to reach 87.5% of the CPSS, I need 3 half-lives. Because 87.5 is in the middle between 75 and 100%. It's in the middle. Okay? So I need 3 half-lives. And to get to maybe 93 point something, I need 4 half-lives. To get almost to 96%, I need how many half-lives? I need 5 half-lives. Okay? So theoretically, I need infinity time to reach the steady state. That's very long time, as we already explained before. With theophylline, I need more than 7 hours just to start getting the effect, even I'm not reaching the CPSS. So we need a solution. What is the solution to get to the steady state quickly? This is what I will discuss now. Look at the figure here again, time in hour and concentration milligram per liter. I am having an infusion starting from 0 and then going up, and slowly it's getting level, يعني straight, getting to that steady state. Why it's getting to the steady state? Why it's leveling? It's because the input will output becomes very close, and eventually they will be the same. طيب, let's say this is your CPSS. This is your desired concentration. And you need to reach it quickly. So what is the solution? We have 2 solutions. One solution is, let us give an IV bolus, so that this IV bolus give us the CPSS at time 0 time. So as soon as I inject, it's 1 compartment, so quickly I will be at CPSS. Now if I don't do anything, I just gave the IV bolus and I don't do anything, what will happen? The concentration will start to decrease. So what do I do after giving an IV bolus? I start giving the infusion at the rate that I already calculated, like for example 60 milligram per hour. So after IV bolus, I will start the infusion. In this way, I can get to CPSS at time 0 and then maintain it. So إذا the first approach, what do I do? Combined infusion with IV bolus administration. إذا بعطي IV bolus, get to the target at time 0, and then maintain it by the IV infusion. طيب, how do I calculate how much dose do I need to give as an IV bolus? How do I calculate that? Remember that I need CPSS at time 0. So how do you calculate the dose for CP0? So your CP0 is actually the same as CPSS. So how do you get your concentration to CP0, the same as CPSS? You remember the equation that CP0 is equal to dose by V. So what do you need? You need to know what is the apparent volume of distribution, what is your target CPSS, because that will be your CP0, and then you can calculate the dose required. Okay? Yani for example, let's say according to theophylline, okay, we agreed that we will use 60 milligram per hour, and that will give us 14.1 milligram per liter. So I will go back to the same example. So what is the same example? Okay, my K0 is 60 milligram per hour, and my CPSS is 14.1 milligram per liter. What do I need to do? I need to give now an IV bolus to reach this CPSS at time 0. So I will say CPSS is equal to my CP0, and CP0 is equal to dose divided by V. طيب يعني 14.1 will be equal to the dose divided by V. What is the V for theophylline? We said that it's 25 liters. So multiply 25 liters by 14.1 milligram per liter, and you will get the dose. So what do you do with that dose? You inject it as an IV bolus, and then start the infusion process at 60 milligram per hour. So this is the first way to deal with the problem. What is the problem? We are taking long time to reach the desired concentration. By doing this, we are reaching the desired concentration immediately. طبعا the problem is sometimes this is not recommended because, as I said in the beginning, if you give an IV bolus in the beginning, there might be a problem because initially the concentration will be high in the blood because it did not really distribute well. It takes maybe several minutes before it really distributes well in the compartment. Okay? So what is the other way? The other way is simple. It's used more frequently. The other way is you need to ask yourself a question. How fast do I need to get to the CPSS? If 0 is not good because it might have some side effects, then how long do you need to infuse the drug in order to reach the CPSS? Now, focus here because some students get confused. Okay? Isn't? You have to ask yourself, theoretically it takes infinity time. Practically, زي في elimination half-life, you need 5 half-lives to approach the steady state. يعني for example, theophylline, 5 half-lives is the half-life of theophylline is 4 hours. 5 half-lives means you need 20 hours to approach the CPSS. طبعا this is very long time. So ask yourself, how fast? Now in many cases they use half an hour or 15 minutes. So they want to approach their desired concentration in maybe, let's say, half an hour. Okay, so I will assume now that I want to reach the CPSS in half an hour. طيب, so in order to do that, I need to make the infusion fast. Okay, to speed up the infusion rate. Speeding up the infusion rate will allow me to reach my target concentration. انتبهوا, I want you to focus on what I will say now. Because if you speed up the infusion rate, this infusion rate which you speeded up, you made it, مثلا, for example, instead of 60, 120, 180, etc., you speeded up the infusion rate, but it will have another CPSS, which will also will take long time to approach. Okay? يعني, I will show you this in a graph. This is time in hour and Cp in milligram per liter. If this is my slow infusion, this is my fast infusion, faster infusion. شوفوا, each one, let's say this is K dash 0, K 2 dash is 0, and this is the original one, K0. Each one has its own CPSS. For each infusion rate, there is CPSS. So what is the idea here? I want to make the infusion rate fast enough to get to the desired concentration quickly, and then I need to slow down the infusion rate. I cannot leave it fast. Why? Because if you leave the fast infusion as it is, the concentration will be higher. As I said in the beginning, if you double infusion rate, CPSS will double, concentrations at all times will double as well. Okay? طيب, فإذا the idea is, okay, this is my CPSS for this slow infusion. Let's say I want to get it at time half an hour. So what do? I use K0 double dash. I make it fast so that in half an hour I get to this concentration, which is my target concentration, and then I have to slow down the infusion rate to K0. K0 will maintain, the input will output will be similar at that concentration. And then I can maintain the concentration at CPSS. This is the idea. So we call it combined fast infusion followed by slow infusion, or original infusion that maintains the concentration at the desired concentration. So what do? You use the following equation, the integrated equation. Cp is equal to K0. I will not call it now CPSS, just not to confuse you. K0 divided by KL/V multiplied into 1 minus ES minus KL/T. This equation will be used for what? My Cp now will be my target concentration, but it's not the CPSS. Why? Because I'm using fast infusion. Fast infusion will give you another CPSS. It's not my target. So my target Cp is equal to the fast infusion, K0 double dash, okay, divided by KL/V multiplied 1 minus ES minus KL/V. Now, this one is my target, اللي هو CPSS تاع ايش؟ of the slow infusion. This is my target. And I need it in half an hour. So I will substitute T with half an hour. So what do I do? My target is 14.1 equal to K0. This is the fast, which I don't know. I need to calculate that. Divided by KL, شو KL اللي هي 0.17 multiplied بالفي اللي هي 25 liters multiplied into 1 minus E us minus KL اللي هي 0.17. هلا multiplied في T اللي هي ايش؟ I said in the beginning we want to reach my target in half an hour. So T is half an hour. Now, the only missing information here is K0. Now you can calculate that and you will find that K0 is equal, let me find out. Yes, it's equal to K fast. K0 fast is equal to how much? To 735 milligram per hour. So this is the fast infusion. Following this fast infusion, for half an hour, I should not leave it at 735 because this will give me another steady state. So after half an hour, I have to slow it down back to 60. If I do that and I slow it down back to 60, what will happen? The input will be equal to the output and the concentration will be maintained at 14.1 milligram per hour. Milligram per liter. Now, suppose you forgot to slow down infusion. You forgot it. You went to home. What will be the CPSS if you continue with this 735 milligram per hour? This is very fast infusion rate. Instead of 60, I'm using 735. So what is the steady state if you use this one? Remember the equation? CPSS is equal to K0, هلا هاي fast. 735 divided by KL اللي هو 0.17 multiplied into apparent volume distribution, and this will give you a concentration of 173 milligram per liter. شوفوا من 14.1 لا 173 milligram per liter. That is very high concentration, much more than the minimum toxic concentration, which means that you need to slow it down at half an hour. At half an hour you will reach your target concentration, so slow down the infusion to the original one. Okay? So this is regarding how to achieve the target concentration of CPSS quickly. What I will discuss now is what happens after I stop. After I stop the concentration, what happens? Sorry, after I stop the infusion, what happens? Is it something will change? I stop the infusion, nothing is getting in. So what happens is only elimination. بتصير So it will be as the same as IV bolus administration. You only have elimination. So how can you deal with that? Now this is what I will discuss. Okay, so what happens when we stop infusion? Suppose we said previously that we want to speed up infusion until we reach our target, the 14.1, and then we want to maintain the infusion by the slow infusion to 60 milligram per hour. Suppose you have speeded up the infusion by using an infusion rate of 735 milligram per hour, and then after half an hour, you switched off the pump and you did not start the slow infusion. So what will happen after that? Let's look at it with the graph. You have time in hour, concentration in milligram per liter. So this is your fast infusion. So in half an hour, you reached 14.1. Then you stopped. You did not start the slow infusion. What will happen? You will have mono-exponential decrease fill concentration. It is like what? Like you are giving an IV bolus and you are waiting for the elimination to happen. So you will have a decrease in the concentration. So how can I calculate the concentrations following or after stopping the infusion rate? We will deal with it as the IV bolus administration, because the only thing that is there is elimination now. So you have the concentration in the body and elimination. Now this point when you stop is special point. I will call it CP, but I will give it T capital, just to say that this is the last point when you stopped. The last point in concentration when you stop, CPT capital. Now, how do you know what is your CPT capital? طبعا, it's because it is the last point in the infusion. We will use the same equation. CPT capital is equal to K0 divided by K alpha V multiplied 1 minus EOS minus K alpha T. What is your K0 here? You use the fast infusion. So it's 735 divided by 0.17 اللي هو ال KL of theophylline multiplied by V اللي هو 25 liters, all multiplied by 1 minus EOS minus KL. Here KL is again 0.17. T is half an hour because that's your infusion. So that's your CPT capital. What happens after that? You have, as I said, you have mono-exponential decrease fill concentration. So if you want to calculate the concentration at any time following stopping the infusion, you will need to multiply, I'm talking here about post-infusion. Okay, you need to multiply your CPT capital and multiply it into E to the power of minus K alpha T. Now, EOS minus K alpha T is the fraction remaining. So remember the IV bolus administration. This is the fraction remaining of CPT capital. The fraction remaining of CPT capital. But this T is, what is this T? It is the time since I stopped the infusion. It's not from the beginning. That's why if you want to use the time from the beginning, then you should say T minus T capital. Why this time is T minus T capital? Why is it like that? It is because I want only the time since I stopped the infusion. So for example, I'll give you an example. Let's say my infusion, as in this example, lasted for half an hour. Okay? And then I stopped. Now from the beginning, beginning means beginning of infusion, and a time of 4.5 hours has passed, or have passed. So actually the time that passed from stopping the infusion is 4 hours. Okay? So from stopping the infusion 4 hours, but from the beginning it's 4.5 hours. So what will be the concentration? So how I do it? Your CPT capital will be 14.1 because actually I started the infusion by fast infusion so that in half an hour I reach 14.1. So that was already explained before. So your CP at 4.5 hours from the starting of infusion, from the beginning, will be equal to CPT capital, which is 14.1, multiplied E us minus K alpha T. But what is this T? And here 4.5? Is it 4.5 or 4? What is it? If you want to use from the stopping of the infusion, then it's 4 hours. If you want to use from 4.5 hours from the start of infusion, then you will have to use T as 4.5 minus half. So 14.1 multiplied E us minus KL, KL is 0.17, multiplied into either you will use 4, that is from stopping the infusion, or you will use 4.5 minus half. So multiplied into 4. Now the answer for this will be about 7.05 milligram per liter. Okay? So if you look at this equation, شو equation اللي هي CP after post infusion. Now I'm talking about post infusion. يعني بعد الانفيوجن, after I finish the infusion, will be equal to CPT capital E us minus KL T. Again, the T here is actually from the stopping of the infusion. طبعا, if you compare it to the IV bolus administration, it's almost the same. Should IV bolus administration will come CP is equal to CP0 E us minus KL T. It's almost the same equation. Okay? طيب, the other thing, or the other example, which is a homework for you, and in this homework, you will need to calculate KL and V. And you will need to use a graph tape. طيب, in this example, it says that there is an infusion of 100 milligram per hour. So K0 is 100 milligram per hour. And it says that there is a data collected post infusion, because the infusion only lasted for 2 hours. Is a T capital addition to T capital, it's 2 hours. Okay, it's lasted for 2 hours. But then they collected data. The data that they collected is from 3 hours onwards. Okay, and they did not even calculate CPT capital. So in this data you have time. Let's just imagine it as a graph. Time in hour with concentration with milligram per liter. Imagine that this is the infusion, and then this is the mono-exponential decrease for concentration. So this is 2 hours, at 2 hours, and then they collected a data starting from 3 hours onwards. So what do you have? You have the concentration at 3 hours, 5 hours, 9 hours, 12 hours, 18 hours, 24 hours. Now this is a homework. So what do you do with this data in order to calculate KEL and V? First, remember that these data that you have in the table, this data will give you a straight line simulograph paper, because it's very similar to IV bolus administration, because the process here is only elimination. So if you take it to a simulograph paper, you plot these data, and when you care about this data, you should get a straight line. So what is the benefit from this straight line? The slope of this straight line will give you KL. So put it in a simulograph paper, draw the best fitting straight line. You want to extrapolate, you can extrapolate, but be cautious. This is not your CP0. What is your CP0? Your CP0 is 0 because remember that in the infusion process at time 0 the concentration is 0. So we actually do not need to extrapolate to y-axis. The most important thing is to extrapolate to CPT capital. That's the important thing. So from 3 hours, where do you extrapolate? Extrapolate till 2 hours. Why you need to extrapolate till 2 hours? Because there where you will have your CPT capital. Okay? طيب, I got my KL from the slope. Slope is equal to minus KL. وبتعرفوا, you know that it's linear concentration 2 minus linear concentration 1 divided by T2 minus T1 will give you a negative value, and then you can get your KL be hour to the power of minus 1. طيب, how do I get V, the apparent volume distribution? Actually, you will get it, and remember this because you will have this in the lab. You get it, you get your CPT capital from the straight line. Even if in your experiment you already have the data for CPT capital, these data are from the table. You don't use the same thing. You have to use CPT capital from the straight line. So get your CPT capital from the straight line, and remember that CPT capital equal to H, K0 divided by KL PV multiplied into 1 minus E us minus KL T, or T capital again, because that's the time when I stop. But look at this equation, look at it. Actually everything is there. CPT capital, you got it from the graph, okay? K0 it's already given, it's 100 milligram per hour. KL you got it from the slope of the straight line. V is the unknown, multiplied into 1 minus E us minus KL. Again, you got KL from the slope. Multiplied with T. What is T capital here? T capital is the time when you stopped. Okay, and when did we stop? It says, the question says, following a 2-hour infusion. معناته, this means that the infusion lasted for 2 hours. So I will put 2 hours here. So the only missing thing here will be your volume of distribution. So now by doing this, you got your KL and you got your apparent volume of distribution. Okay, by this video, we completed now the intravenous infusion topic or unit. Thank you so much. And if you have any question, again, you are always welcome to my office, discuss anything. I'll be happy to answer you and explain to you anything.